We've spent 2 sessions trying to assimilate basic ideas on motion. More specifically, motion in one dimension, particle moving along a straight line, right? And one dimension motion essentially would have 3 categories. For a particle moving along a straight line, it would have 3 categories. Category 1 would be a particle moving with constant velocity, right? That would be category 1. And for a particle moving with constant velocity, the velocity time graph looked like this. This was the velocity time graph, right? And from in a given interval, say 0 to t naught, the area under the velocity time graph gave us what? Displacement. The slope of the velocity time graph gave us the acceleration. For a line parallel to the horizontal axis, the slope of the line is going to be 0. That's because acceleration of this particle is 0. If a particle is moving with constant velocity, its acceleration is 0, right? Realize also that this is v versus t. If I have to draw 1 by v versus displacement s, what would be the graph of the reciprocal of the velocity versus displacement? Hey, if velocity remains constant, 1 by velocity also remains constant. If velocity remains constant, 1 by velocity will also remain constant. So even though the particle undergoes a displacement, the graph of 1 by velocity is also a constant graph. And so from 0 to s naught, if s naught is the displacement, right, then this length will be 1 by v. This would be 1 by v, say the velocity is at this point 1 by v naught. V naught is the constant velocity with which the particle is moving. Then this length would be 1 by v naught. This length would be 1 by v naught. And the area under the 1 by v versus s graph would be what? This area, as you can see, is 1 by v naught into s naught. That's the area under the 1 by velocity displacement graph. But s naught by v naught is the time taken. S naught by v naught is the time taken, t naught, right? So area under 1 by v versus s graph will give you the time. Reciprocal of the velocity versus displacement, the area under that graph will give you what? The time taken for that displacement. Will give you the time taken for that displacement. Yes or no? Right? Now, whatever I have said of the constant velocity situation is also true in principle for constant acceleration. Again, all one-dimensional motion, particle moving along a straight line. So if we had, say, constant acceleration, then I mentioned to you that there were 3 equations of motion that we obtained for a particle with constant acceleration. Velocity t seconds after t equal to 0, where u was the velocity at t equal to 0, was given by u plus at. Displacement in t seconds, algebraic displacement, ut plus half at squared, and v squared minus u squared is 2ax, right? These were algebraic entities like I mentioned to you. All quantities used here were algebraic and they had to be assigned suitable signs, right? Again, velocity versus time is going to be a straight line, because if v is plotted in the y direction, t is plotted in the x direction, then this is of the form y equal to mx plus c. M, the slope, will represent the acceleration, right? So velocity time graph for such a situation would be a straight line. Like I said, the area under the velocity time graph will, like before, will still give you the displacement. The slope of the velocity time graph will give you the, in this case, say theta is the angle that this line makes with the positive direction of the horizontal axis, then m equal to tan theta will give you the acceleration of the motion if velocity versus time was a straight line, right? And the area under velocity time graph will give you the displacement. Also in a given interval, if u was the velocity at the beginning of the interval, v velocity at the end of the interval, then I told you that u plus v by 2 will also measure the average velocity. But the fundamental definition of average velocity is total displacement by total time. And it so happens that in a given interval, the total displacement by total time for a constant acceleration case is also velocity at the beginning of the interval plus velocity at the end of the interval divided by 2. That will also give you the average velocity. But that's not the definition of average velocity. It so happens that it turns out to be equal to that for a constant acceleration case, right? So that was velocity time graph, right? Area under the velocity time graph was displacement. Again, let me tell you that yeah, please come in. That in a constant acceleration case, the displacement time graph, the displacement time graph, displacement versus t is not going to be a straight line because there are square terms. Displacement is a quadratic in time, and the displacement time graph now will not be a straight line. It's going to be a curve. Now this curve could be like this, which we learn later is a parabola. This displacement time graph would be a parabola if acceleration is constant. It could have a shape like this, or it could also be like this. The displacement time graph could be like this, or it could be like this. There are two possibilities. Now, what's the difference between the two graphs? So, one of the things that I need to tell you here is that in general, whether it's constant acceleration or not constant acceleration, if for a particle moving along a straight line, if somebody gave you the displacement time variation, if somebody gave you the displacement versus time variation graph, right, then at a given point P, at a given instant of time T, the velocity at the instant of time T, look at the corresponding point on the graph of this function. And at that point, draw a tangent. This is the tangent at P. Tangent to the curve at P. This tangent will make an angle theta with the horizontal axis, with the positive t direction. This tangent will make an angle theta with the positive t direction. And the slope of this tangent, which is tan theta, will give me the velocity at an instant of time t. The slope of this tangent will give me the velocity at an instant of time t. This will give me the velocity of the particle at an instant of time t. So, if the slope is higher, the velocity will be higher. If the slope is higher, the velocity will be higher. All right. And in notation of calculus, the slope of displacement time graph Vt is also given by dx dt. So this tan theta is also the value of dx dt at an instant of time t. This velocity at an instant of time t, which is dx dt, is the slope of the displacement time graph at an instant of time t. Right? Now this irrespective of whether it's constant acceleration or not, no matter how displacement time is varying for a particle moving along a straight line, if at any given instant of time you have to find the velocity, what would you do? You would draw a tangent at that point. Then the slope of the tangent tan theta will give you the velocity at that instant. And in calculus notation, it's also given by dx dt or ddt of x at an instant of time t. Now, having said this, can I wipe this off? Right? See, look at these two variations. Look at these two variations and let's try and understand what's the difference between these two graphs. Let's try and understand. Say again, for constant acceleration, like I said, displacement versus time is going to be a parabola, For a constant acceleration, we will learn that if x varies as a quadratic in t, then displacement time is going to be a parabola. Now, whatever, that's a name as far as you are concerned. As of now, it's just a curve whose name I have told is a parabola. That's all. But it's a curve. It's not a straight line. That's what you, for the time being, assimilate. But what's the difference between this and this? Let's try and understand the difference between this. In this case also displacement is increasing with time. In this case also displacement is increasing with time, say for example, right? What's the difference between these two? See, in this case, if at this instant of time, if I draw a tangent, this is the tangent at this instant of time, right? At a later instant of time, so this is at t1, this is the tangent. The slope of this tangent will give me the velocity at t1. Look at another instant of time, t2, a later instant of time, t2, and draw a tangent at this instant. Draw a tangent at this instant. Then the slope of the tangent at t2 will give me the velocity at t2, yes or no? If m1 is the slope at t1 and m2 is the slope at t2, then m1 will give me the velocity at t1, m2 will give me the velocity at t2. Yes or no? Okay, tell me this. If I give you in the xy plane two lines, one like this and the other one like this, which one has greater slope? Second one, because see, if this makes an angle theta 1 with the horizontal axis and this makes an angle theta 2 with the horizontal axis, then very clearly theta 2 is more than theta 1. Theta 2 is more than theta 1, right? In this case, this line is more vertical than this line. See, loosely speaking, this line is more vertical than this line, isn't it? Is more vertical than this line. This line is more horizontal, this line is more vertical. So theta 2 more than theta 1. So tan theta 2 will be more than tan theta 1. Tan theta 2 is the slope of this line, m2. So m2 is more than m1. Yes or no? If a line is more vertical, then it will have a greater slope. If a line is more vertical, it will have a greater slope, greater magnitude of slope at least. If one line is more vertical than another line, then the magnitude of slope of that line will be more than the magnitude of slope of the other line. Do you understand this fact, right? So now, look, this line, this tangent is a line after all, right? This tangent, which is a tangent at t equal to t1. And it has slope m1. And m1 gives me what? Velocity at t1. This is m2, slope of the line at t equal to, slope of the tangent at t equal to t2. And what would m2 give me? Slope of the tangent at t2, and which in turn is the velocity at t2. m1 is the velocity at t1, m2 is the velocity at t2. As you can see, the tangent at t2 is more vertical than the tangent at t1. Do you see that? The tangent at t2 is more vertical than the tangent at t1. Right? So m2 is more than m1, isn't it? In this graph, m2 is more than m1. That means velocity at t2 is more than velocity at t1. Yes or no? That means this is a graph in which the velocity is constantly increasing. This is a graph in which the velocity is increasing. Yes or no? Right? In contrast, look at this. Because the tangents are becoming more and more vertical in this case, what is happening to the tangents? Tangents are becoming more and more vertical. So velocities are increasing. Do you see that? Velocities are increasing with time. Right? So it's a case of acceleration. It's a case of acceleration because velocities are increasing. If this was the shape of the displacement time graph, if this was the look of the parabola, then it's a case of increasing velocity because tangents are becoming more and more vertical. It's a case of acceleration, right? Now let's explore this. Can I just remove the clutter from here? If I had displacement time which looked like this, which is also a parabola, a case of constant acceleration. If displacement time is a parabola, it must be a case of constant acceleration, right? Now, this is time t equal to t1, right? At this point, if I draw a tangent, what will I get? The velocity at t1. Slope of this tangent will give me what? If m1 is the slope of this tangent, what would it give me? It will give me velocity at t1, right? Let me move to some other instant of time. t2. m2 is the slope of this line, slope of the tangent at t2. What would m2 give me? Velocity at t2. Now, so m1 gives me velocity at t1, m2 gives me velocity at t2. Which of the two tangents is more vertical? m1 is more vertical than m2. m1 is more vertical than m2. Do you see that? So, can I say if m1 is more vertical than t1, then m1 is more than m2? Yes or no? m1 is more than m2. That means velocity at t1 is more than velocity at t2. Yes or no? That means as time increases, velocity is decreasing. This is a case where velocity is decreasing. And if velocity is decreasing, it must be a case of retardation. It must be a case of retardation. This means retardation. The earlier one was a case of increasing velocity, that was acceleration. This is a case of decreasing velocity, so it's a case of retardation. So do you understand the difference between the earlier displacement time graph and this displacement time graph for constant acceleration? Both are parabolas, but one represented increasing velocities and therefore acceleration. The other one represented decreasing velocities or retardation. Yes or no? Right now? Also, can I wipe this off? Yes, yes. For a particle moving along a straight line, if displacement time graph is a parabola, it has to be a case of constant acceleration. It has to be a case of constant acceleration. Has to be. No issue so far, right? Now, acceleration time graph. See, for a constant velocity, for a case of constant velocity, what's the acceleration time graph? This. Acceleration is 0. Acceleration is 0 at all times. This is the acceleration time graph, right? For a particle moving with constant velocity, this is the acceleration time graph, right? For constant acceleration which is non-zero, this is the acceleration versus time graph. Yes or no? This is the acceleration time graph. And this is the value of the acceleration, which remains A at all times. Acceleration remains A at all times. Now, what is this area? A into T. Yes or no? This area is A into T. This area is A into T. Hey, but A into T is V minus U. V is U plus AT, isn't it? So A into T is V minus U. So this is V minus U, which is change in velocity, which is change in velocity. So area under the acceleration time graph, area under the acceleration time graph will always be change in velocity. Will all see in this case, look at the constant velocity case. The area under the acceleration time graph is 0, so change in velocity is 0. Do you see that? Area under the acceleration time graph is 0, so change in velocity is 0. That's because it has constant velocity. So change in velocity ought to have been 0. Yes or no? Do you all understand this? Huh? So 1. And what I have said of constant acceleration will also be true if the acceleration is not constant. Area under the acceleration time graph will always be change in velocity irrespective of whether it's constant acceleration or not constant acceleration. What I mean is, suppose there was a case where the acceleration was not constant but varying. And by the way, if acceleration is not constant, you don't apply these equations of motion, right? If acceleration is varying with time, acceleration is varying with time, say, it's not a case, this is not a case of constant acceleration. This is not a case of constant acceleration. So in a given interval, say 0 to t, this is the area under the acceleration time graph. This is the area under the acceleration time graph, right? And this area represents change in velocity. In the given interval. This will represent change in velocity in the given interval. Yes or no? So irrespective of whether acceleration is constant or not, area under acceleration time graph will always represent change in velocity in a one-dimensional scenario, right? Makes sense to all of you, right? Which means, say, suppose acceleration versus time graph was like this, and this is t equal to 1, and this is say t equal to 2. And say this angle is 60 degrees. This angle is 60 degrees. Say it's a straight line. Obviously, it's not a case of constant acceleration. It's not a case of constant acceleration. Now, between t equal to 1 to t equal to 2, I want to find the change in velocity. Velocity at t equal to 1 says v1, velocity at t equal to 2 is v2. And I want to find the change in velocity, v2 minus v1. What would that be? That would be this area. That would be this area. This area would be v2 minus v1, change in velocity. Yes or no? Now, very easy to find that. Hey, this length. See, this is 1 unit. So this would be 1 tan 60 degrees. This height would be 1 into, because this is 1 unit, this is 60 degrees, this would be 1 tan 60 degrees. So 1 tan 60 degrees means root 3. Right? Okay. Now this is 2 units, and this would be 2 tan 60 degrees. This would be 2 tan 60 degrees. This is 2 units. Perpendicular by 2 is tan 60 degrees. This length by 2 units is tan 60 degrees. So this length must be 2 tan 60 degrees, isn't it? Look at this right angle triangle. So this is 2 tan 60 degrees means 2 root 3. And what's this area? This area is, this area A is, this is a trapezium. Average of parallel sides into distance between them. Average of parallel sides means 2 root 3 plus root 3 by 2. That's the average of parallel sides into distance, 1 unit between them. And this would represent v2 minus v1, change in velocity. This will represent v2 minus v1, which is change in velocity. which is delta v. Change in velocity, which is delta v. Yes or no? So whether acceleration is constant or not, in a one-dimensional scenario, area under the acceleration time graph will always represent change in velocity. Also tell you that whether velocity is constant or not, the thing that you must know is, see, for a constant velocity we found that the area under 1 by v versus s represented the time taken for that displacement, isn't it? Even if velocity was not constant, if velocity is not constant, 1 by v will also not be constant. So if I had, in a very general scenario, 1 by v varying, say if 1 by v versus displacement s is non-uniform, is this, this is s equal to s1, this is s equal to s2, right? If 1 by v versus s is this, then this area will give me, this area will always give me time taken for displacement. What's the net displacement? S2 minus S1 will give me the time taken for the displacement S2 minus S1. This area will always give me time taken for displacement S2 minus S1. Yes or no? Got me? So for all cases in one-dimensional situation, 1 by v versus s, if that graph is known to you, then the area under 1 by v versus s graph will always give you the time taken for the corresponding displacement. In this case, the displacement is s2 minus s1. Yes or no? And see, in a case of constant acceleration, velocity versus time is a straight line. This is a case of constant acceleration. Velocity versus time is a straight line. But if acceleration is varying, then velocity time will not be a straight line. If acceleration is varying, then velocity time graph will not be a straight line. If acceleration is varying, in general, velocity time graph will be a curve. This is a case of variable acceleration. This is a case of variable acceleration. This is a case of variable acceleration. Velocity time, if it's a straight line, it has to be constant acceleration. For constant acceleration, Vt will be a straight line. But if Vt is not a straight line, acceleration is not constant. Acceleration changes from instant to instant. Acceleration changes from instant to instant, right? So in this case, if at an instant of time t1, if I have to find the acceleration, then the acceleration will be given by the slope of the velocity time graph. That means this is the tangent drawn at t1. This is the tangent drawn at t1. And its slope is m1. The slope of this tangent is m1. And this m1 will give me the acceleration at t1. Slope of the velocity time graph. When I say slope of the velocity time graph, what does it mean? It means slope of the tangent to the curve. It means slope of the tangent to the curve. So at t equal to t1, if I have to find the acceleration in the velocity time graph, then at that point I draw a tangent. The slope of this tangent m1 will give me the acceleration a1 at t1. This will give me the acceleration a1 at an instant of time t1. Suppose this is time t equal to t2. At this case, in this case, if I have to find the acceleration at t2, I draw the slope of the acceleration velocity time graph. I draw the tangent at t equal to t2. I draw the tangent at t equal to t2. This is the tangent at t equal to t2. And this tangent has slope m2. And what would this m2 give me? Acceleration at t2. This m2 will give me acceleration at t2. Now in this case, for the given figure, can you tell me which one is bigger, a1 or a2? A2 is bigger, because realize that slope of this tangent is more than slope of this tangent. Why? Because this tangent is more vertical than this tangent. If a tangent becomes more vertical, if a line becomes more vertical, then the magnitude of its slope will be higher. So M2 is more than M1. Do you realize that? So A2 will be more than A1. So this is a case of increasing acceleration. It's a case of increasing acceleration. Yes or no? Right now? Because the tangents are progressively becoming more and more vertical. If the tangents are becoming more and more vertical, accelerations are growing in stature. Accelerations are growing in magnitude. Yes or no? Right? So if this was the velocity, and of course, it's not a case of constant acceleration, as you can see. Right? Can I wipe this off? Suppose the velocity time graph, instead of the earlier diagram, if it was like this, suppose this was the velocity time graph, then at any given instant of time t1, how do you get the acceleration? Draw a tangent at that point and the slope of the tangent will give you the acceleration. At t equal to t2, the slope of the tangent at t equal to t2 will give you the acceleration at t2. Yes or no? Now, if m1 is the slope of the tangent at t1, if m2 is the slope of the tangent at t2, which one is more, m2 or m1? M1 is more than m2, because m1 is, this tangent is more vertical than this tangent. So m1 is more than m2. But what does m1 represent? Acceleration at t1. And what does m2 represent? Acceleration at t2. So this is a case where accelerations are decreasing. This is a case where accelerations are decreasing. Yes or no? The earlier was the case where accelerations were increasing. Yes or no? Got me, no? Now, let me also tell you another jargon associated with, but so far so good. Do you understand everything that I'm saying, right? This is a case of decreasing acceleration. The earlier one was a case of increasing acceleration. Now, see, there were two cases I discussed for velocity time. This was one case, and in this case the tangents were becoming more and more vertical, so acceleration was increasing in magnitude. This was a case where the velocity time graph was like this. In this case, the tangents are becoming more and more horizontal, so accelerations are decreasing. This is a case where acceleration is increasing. This is a case where acceleration is decreasing. Yes or no? Now these two curves, in both cases velocities are increasing. In both cases velocities are increasing with time. Do you see that? But in this case acceleration is increasing. In this case acceleration is decreasing. Right? Now, these are two different shapes. For an increasing velocity, I can have two distinct shapes. This is one shape and this is another shape. What's the difference between the two shapes? In this case, if you draw a tangent at any point, then the tangent is below the curve. Do you see that? If you draw a tangent at any point of this curve, then the tangent is below the curve. Yes or no? Do you realize that? Tangent is below the curve in this case. Right now? Whereas in this case, if you draw a tangent at any point, tangent is above the curve. Do you see that? In both cases, the slope of the tangent represents the acceleration at that instant, is above the curve. Right? Yes or no? Now this shape where the tangent is below the curve is called a concave shape. If a curve is such that the tangents are below the curve, then that shape is a concave shape. This is a shape where the tangents are above the curve. This shape is called a convex shape. This is called a convex shape. This curve is called a convex curve. This curve is called a concave curve. In a concave curve, the tangents are below the curve. In a convex curve, the tangents are above the curve. Yes or no? Do you all get me right on this? No confusion? Oh, okay. Now, it still has acceleration. Velocity is increasing but at a decreasing rate. Isn't it? His question is, if the accelerations are decreasing, how could the velocity increase? Why not? There's a particle moving in a straight line. First, it has an acceleration of 5 meters per second squared. It starts from rest. At t equal to 1 second onwards, it has an acceleration of 3 meters per second squared. At t equal to 2 seconds, again its acceleration becomes a3 equal to 2 meters per second squared. Hey, accelerations are decreasing, but they still are accelerations. Velocity will still be increasing, isn't it? From here to here, will there be increase in velocity? Yes. From here to here, will there be an increase in velocity? Yes, because there still is an acceleration. Although, in this 1 second, the increase in velocity will be more than the increase in velocity here. Yes or no? Because it has lower acceleration. So, change in velocity here will be more than change in velocity here. But in both cases, there is increase in velocity. The increase in velocity here will be more than the increase in velocity here. That's the only thing. But in both the intervals, there would be increase of velocity. Got me, no? Clear? You got me right on this, right? Huh? So now, with some of these things set up right, eventually, when we talk of motion, I've spoken of one-dimensional motion, right? Where the particle is moving along a straight line. That straight line could be the x-axis, could be the y-axis, or could be any other line, right? Say, for example, a particle could be moving in the xy plane. This is the trajectory of a particle moving in the xy plane, say. Say y equal to 2x plus 3 is the trajectory of a particle, which is a straight line. Now, to determine any point on this trajectory, would you need x and y both? No. If you just had the value of x, y would automatically be determined. So how many independent entities are required to locate the particle? Just one. Either you know x or you know y, the other one would be known to you. So if only one independent entity is required to locate the particle, then the motion is one-dimensional. Don't think that because it's moving along a straight line y equal to 2x plus 3, the motion is two-dimensional. No. The motion, it's along a straight line. That straight line could be anything. And only one coordinate is enough to locate the particle. So that's a straight line motion, right? Now, suppose at a given instant of time, the velocity in the x direction, is given to be 3 meters per second. Suppose at a given instant of time, the velocity in the x direction is 3 meters per second. What would be the velocity in the y direction? What would be the velocity in the y direction? Look, y is 2x plus 3. dy dt will give me velocity in the y direction. dy dt will give me velocity in the y direction. Yes or no? By definition, rate of change of displacement in the y direction will give me velocity in the y direction. Yes or no? That's equal to 2 times dx dt, differentiating both with respect to time, and derivative of 3 is 0. Yes or no? It's a constant. If I differentiate both sides with respect to time, then dy dt would be 2 times dx dt plus ddt of 3, which is 0. Yes or no? Do you understand this? But what is dx dt? Rate at which displacement occurs in the x direction, that's going to be vx. Yes or no? Dy dt is velocity in the y direction. Dx dt is velocity in the x direction. Yes or no? And this is given to be 3 meters per second. So this is 6 meters per second. That's the velocity in the y direction, right? Velocity in the y direction is 6 meters per second. And we know that the particle is moving along this line. That means the resultant of Vx and Vy must be along this line. The resultant of Vx and Vy must be along this line. And the net velocity of the particle, V, is given by root Vx squared plus Vy squared. Vx squared is 9 and Vy squared is 36. That means root 45, which is 3 root 5 meters per second is the net velocity of the particle. Is the net velocity of the particle. Yes or no?